Hello, welcome to es346 Basic Thermodynamics. These are examples, and the example today we're going to look at is the second law efficiency of a Rankine cycle. I'm Mark Peterson. So here's the example we're going to look. We have a Rankine power cycle, and we're told that it delivers 5 megawatts of power while receiving 12.3 megawatts of heat input. The boiler operates at 1000 degrees Fahrenheit and the condenser operates at 50 degrees Fahrenheit. And we're asked to find the second law efficiency for this power plant. Alright, so let's talk a little bit about the background of this first. And what I show on the right here, this diagram, is what's called a simple Rankine cycle. It's got all the basic components of a Rankine cycle, where we've got water as the working fluid, and we have a pump, and it takes liquid water up to a higher pressure, so I'll call that P high, and it starts off at a low pressure, P low. Then that liquid water runs through a boiler where it becomes a vapor, usually a superheated vapor. So it's very hot and still at a high pressure, so I'll call that P high and T high. So this is a superheated vapor. And now that superheated vapor is run through a turbine that generates electric power, and then what comes out is then run through a condenser so it can go ahead and return to a liquid state again. So that's what the condenser does. If we look at what this looks like qualitatively on, for example, a TV diagram, so we have the temperature versus the specific volume, and I'll draw up the saturation curve here. Out of the condenser, what's coming out of the condenser is a saturated liquid normally. So at some point, for example, right there, and I can go ahead and label that 0.1. Then the pump goes ahead and moves it up to a higher pressure. You know, I'm compressing liquid, and the temperature barely goes up at all. It goes up just a teeny bit. So 0.2 is just above 0.1, and it's an incompressible liquid, so the specific volume doesn't change much. It might get a little bit smaller, so it might be tilted a little bit to the right. Then the important step here is running through the boiler, where I take a liquid, I turn it into vapor, and then I superheat it. And so if I was to kind of sketch this process, it sort of runs along the line, it hits this as a saturated liquid, becomes a saturated vapor, and then boils. And so this would be my superheated vapor. And so it's up there, and that would be about 0.3. Then we run through the turbine. The turbine is going to extract power. We're going to lose enthalpy. It's going to be turning into electricity. The temperature is going to drop, the specific volume is going to increase, and so 0.4 might be, for example, down there at some point where it now enters the condenser, and this is at that low pressure, becomes a saturated vapor, and then eventually becomes a saturated liquid. So this is called the Rankine power cycle, and if you continue on in thermodynamics, you'll look at this in more detail. But let's kind of look at this problem where we've got some numbers here, and we're told that this boiler operates at 1000. So this up here is operating at 1000 degrees Fahrenheit. So I realize that I've got liquid water coming into this boiler. So maybe I'll kind of sketch up a boiler here. Consider this our boiler. And I've got liquid water coming in. And that liquid water is initially the first coming in at 50 degrees Fahrenheit. And the boiler is operating at 1000. So when the vapor that's coming out of this, we could imagine, is at 1000 degrees Fahrenheit. Now let's consider, for example, a single pound of water. So the first pound of water comes in here. So we'll just have a little single pound of water. And that pound of water initially is at 50 degrees. And so the very first BTU of energy it absorbs, it's absorbing it from 1000 degree boiler, because the whole boiler is operating at 1000, yet it's only at 50. So if we think about the entropy that's being generated on this, let's kind of go back to this kind of classic idea where I have 1000 degrees Fahrenheit, which is my high temperature source, and then when I'm dumping heat into a 50 degree sink, which is my water, and I have 1 BTU of energy going in there. Now I've got energy leaving high temperature going into a low temperature. It's a big temperature differential. I'm actually generating a lot of entropy. And in fact, we could go ahead and find out what our change in entropy is, right? Because we know that the change in entropy is going to be Q over T. So now, since I'm only considering a single BTU, the temperature is going to be more or less constant. So we could quantify this as the 1 BTU that leaves, and it's leaving at 1000 or 1460 Rankine, because we need to do that in absolute. And then that single BTU is then going into this at 50 degrees Fahrenheit, or 610 Rankine. And so if I know what the generation of entropy is, the entropy that's being generated just by that single BTU is, oops, I got an extra 0 there. Let me erase that. Go. It's 0.00128 units would be BTUs per Rankine, and that's the entropy being generated just by moving that single BTU. So the exergy that's destroyed, I'll call that X sub D, is T naught, the entropy that is generated. And so the environment, let's assume our environment's also at this 50 degrees Fahrenheit. This is the entropy being generated. I could look at the exergy being destroyed. That would be 610. I need to put that in absolute, so that's at 50 degrees Fahrenheit. And 0.00128 BTUs per Rankine. And if I multiply those two numbers together, I get 0.651 BTUs. So what does that tell me? Well, that tells me when I went ahead and moved 1 BTU of energy from a high temperature to lower temperature, I destroyed about 65% of it, of that energy that went into here. It isn't actually going to be work potential. Now, if I want to know the total amount of exergy destroyed, we just looked at 1 BTU going into a single pound. I would need to kind of keep computing as imagine this is my material is moving through and going along here and along here and along here, and I could sum up all of those, and then I'd need to do it for the rest of the cycle. And it turns out that would be kind of a long, arduous process, but we can actually solve this a little bit simpler given the numbers that we have. And so let's go ahead and do that. I'm going to go ahead and give myself a new piece of paper over here. And so if first let's think about what the ideal cycle would look like. And so if I had the ideal cycle, which would be the Carnot cycle operating in the TV range, we know that it has constant temperatures of, this would be my high temperature down here and my T low right there. And this cycle is perfect. This destroys no exergy at all. So the exergy destroyed there is 0 because it generates no entropy. Now to find the efficiency of that cycle, well, that's the Carnot efficiency. That will be 1 minus T low over T high. So we can put on our numbers for our comparing it with our boiler. That's going to be 1 minus so it'll be 510 over 1460. And so the efficiency of that is about 65%. So that's the efficiency of a Rankine cycle operating under the same conditions. Now, what does our actual cycle operate underneath? Well, we're given some information there. We're told that it deliberates 5 megawatts of power when it brings in 12.3. So here's the 12.3 megawatts coming in as the heat input. There's the work output. That's the 5 megawatts. And so there's a little work input here. Right now, we'll go ahead and just assume that this turbine is actually running the pump, so there's actually not a network input in there. So this would be the net work being delivered is at 5 megawatts. So, well, the efficiency of that cycle is, well, what's desired over required. And what's desired out of our power plant would be that 5 megawatts. And what's required is what goes in, which is a 12.3 megawatts. So the actual efficiency of this cycle right here is 0.41 or 41%. And now if I want to know the second law efficiency, I'm just going to take the ratio of those two numbers. Because I'm generating 41%. I could have done 65%. So if I do 41 over 65, that's going to give me 0.63 or 63%. So therefore, my second law efficiency of this cycle is 63%. The best it could do is operate at a total thermal efficiency of 65%. It's only getting 63% of 65%, which is this 41% right down here. So, all right, so that goes ahead and concludes that problem.